Hi, I'm Spencer Everett. I'm a fifth-year PhD student in the physics department at UC Santa Cruz for a few more months before starting a postdoc at NASA's Jet Propulsion Laboratory. I'm a cosmologist, which means I study the origin and evolution of the universe, and in particular, the growth of the large-scale structures of galaxies that we see in the sky today. While they may look randomly scattered throughout the sky, there are subtle patterns in the clustering of galaxies that reveal an underlying cosmic web that has grown from very small variations in the matter density of the early universe, right after its creation in the Big Bang. What kinds of structures formed and how quickly they formed is driven by the components of the universe, such as the light and normal matter we interact with every day. However, decades of observations tell us that the stuff we're familiar with, like the planets, stars, and galaxies, simply isn't enough to account for how much structure we see today. Only about 15% of the matter and 5% of the total energy. We call the mysterious missing stuff dark matter and dark energy. Luckily, the distribution of galaxies holds the information needed to answer some pretty fundamental questions about the universe we all live in. How much dark matter and dark energy is there? What are their properties? And does dark energy change over time? To help answer these questions, I spend my time as a researcher building a census of all the galaxies across 1/8 of the sky as a part of the Dark Energy Survey. We are a collaboration of hundreds of scientists across the world that took over 200,000 pictures with a 4-meter telescope in the Chilean desert. We built sophisticated image processing tools to build an enormous mosaic of over 700 million galaxies, and then spent years of work building probabilistic models that tell us how the properties and distribution of these galaxies rule out certain theories of dark matter and dark energy. In order to answer these questions precisely, there's one huge problem. The process of capturing the set of real objects in the universe with noisy images, complicated software algorithms, and incorrect modeling choices leads to systematic biases in the recovered cosmological parameters that are larger than the usual statistical uncertainty. To tackle this problem, I led a team of scientists on a project called Balrog, which takes very high-quality measurements of a subset of galaxies and injects or adds them on top of the real images across the rest of the survey. As we have very good estimates for the true properties of these injected galaxies, we can map how our complicated analysis modulates the true property distribution of galaxies in the universe into the measured quantities that we see in our data. This allows us to naturally account for the many difficult, subtle, and even unknown systematic errors in our analysis and extract the maximum amount of cosmological information from our data. Without such a careful examination of the systematics of our survey, we could not have produced the tightest cosmological constraints from any galaxy survey ever.